Imitation learning bypasses the complex reward engineering required by reinforcement learning. Instead of defining a scalar feedback function, imitation learning trains a policy directly from expert trajectories. An expert trajectory is a sequence of state action pairs collected from a human operator or a pre-programmed controller. The goal is to minimize the discrepancy between the learned policy and the expert policy. This is fundamentally a supervised learning problem, treating the expert actions as ground truth labels for observed states. This approach is highly effective for tasks where defining a dense reward function is intractable, such as complex human-like manipulation or precise driving maneuvers. The simplest and most widely used form of imitation learning is behavior cloning. Behavior cloning models the expert policy using a neural network, typically a multi-layer perceptron or a recurrent network, depending on the state representation. The training objective is to minimize the empirical risk over the collected expert dataset. For continuous action spaces, this usually involves minimizing the mean squared error between the predicted action and the expert action. This measures the Euclidean distance between the outputs. For discrete actions, the objective shifts to minimizing the cross-entropy loss, effectively learning a probability distribution over possible actions given the current state. Behavior cloning assumes that the expert data perfectly covers all necessary state transitions and that the state space is Markovian. The quality and coverage of the expert dataset are paramount for successful deployment. Behavior cloning is highly sensitive to the distribution of states encountered during training. If the robot deviates even slightly from the expert trajectory during deployment, it enters an unseen state. Since the policy was never trained on this novel state, the resulting action is often arbitrary or catastrophic, leading to rapid compounding errors. This dependency necessitates large, diverse datasets, often collected through teleoperation or kinesthetic teaching. The expert must demonstrate not only successful task completion, but also robust recovery strategies for minor perturbations to ensure generalization.
The fundamental limitation of behavior cloning is covariate shift, also known as distributional shift. During training, the policy is conditioned on states sampled exclusively from the expert's state distribution. However, during deployment, the imperfect learned policy generates its own trajectory, leading to a new state distribution. Because the learned policy is imperfect, this new state distribution quickly diverges from the expert's distribution. The model encounters states where the training data provides no guidance, causing the policy to drift further away. This positive feedback loop of error accumulation makes long-horizon tasks extremely challenging for pure behavior cloning implementations. Dataset Aggregation, or DAgger, provides an iterative solution to mitigate covariant shift. DAgger actively queries the expert for labels and states where the current learned policy deviates from the optimal path. The process starts with the initial expert dataset. The current policy is deployed, and whenever it encounters a state, the expert provides the optimal action for that state. This new state action pair is immediately aggregated into the growing dataset. The policy is then retrained on the combined expanded dataset. This ensures that the training distribution gradually covers the states encountered by the imperfect learned policy, effectively closing the loop and stabilizing performance over successive iterations. Moving beyond supervised learning, Generative Adversarial Imitation Learning, or GAIL, frames imitation learning as an inverse reinforcement learning problem solved using generative adversarial networks. Generative Adversarial Imitation Learning seeks a policy that generates trajectories statistically indistinguishable from the expert trajectories. It employs two components, a generator, which is the policy itself, and a discriminator. The discriminator is trained to distinguish between states visited by the expert and states visited by the generator policy. The generator is trained to maximize the probability that the discriminator misclassifies its generated states as expert states.
The Generative Adversarial Imitation Learning objective minimizes the Jensen-Shannon divergence between the expert state action visitation distribution and the policy state action visitation distribution. The discriminator loss is typically a binary classification loss, maximizing the log probability of correctly identifying expert samples and minimizing the log probability of identifying policy samples. The generator policy is updated using policy gradient methods, treating the discriminator output as a dynamic reward signal. This reward is high when the policy generates actions that successfully fool the discriminator into believing they came from the expert, providing a dense implicit reward structure without manual design. Imitation learning is crucial for robotic tasks requiring fine motor skills and compliance, where analytical modeling is extremely difficult. In robotic manipulation, imitation learning enables learning complex grasping strategies, such as pouring liquids or folding deformable objects, directly from human demonstrations.
For legged locomotion, behavior cloning provides robust initialization policies for complex gaits, significantly accelerating subsequent reinforcement learning fine-tuning. Imitation learning is also foundational in autonomous driving systems, where policies are trained on massive datasets of human driving behavior to handle routine navigation and lane keeping, providing a reliable baseline for safety-critical decision-making. Despite its successes, imitation learning remains constrained by the need for high-quality expert data and the inherent difficulty in generalizing beyond the demonstrated distribution. Future research focuses heavily on combining imitation learning with reinforcement learning, often termed apprenticeship learning, to allow the agent to explore and refine the demonstrated skills autonomously. Furthermore, efforts are directed towards leveraging multimodal inputs, such as vision and haptics, and developing methods for learning from suboptimal or noisy demonstrations. This reduces the reliance on perfectly curated expert trajectories and increases the scalability of data collection.